In this class, we are going to discuss a new topic, the scattering theory. Our understanding about the structure of matter is extracted from the scattering of particles. It is through the scattering experiments that important building blocks of matter, such as the atomic nucleus, the nucleons, and the various quarks, have been discovered. In a typical scattering experiment, one observes the collision between a beam of incident particles like this and a target material. After the scattering, the particles that do not interact with the target continue their motion undisturbed in the forward direction. But those that interact with the target get scattered at some angles. So this is what we are going to consider in this lecture. So we have a beam of incident particles and a target molecule or a target material which interact with each other. And what we are going to analyze is the after effects of this interaction of incident beam of particles and the target materials. So let's consider a beam of particles moving along the z direction. Let's say this is our z direction for convenience, with a flux Ji particles per unit area. So on incident sides we have Ji particles per unit area per unit time. Then we define something called the differential scattering cross section, which we write as d sigma by d omega. This is as the ratio between the number of particles scattered into a solid angle d omega per unit time. So on denominator we have the number of particles scattered into solid angle d omega per unit time. To the number of incident particles crossing unit area in unit time. So what we are considering a beam of particles which is moving along this direction. We take conventionally for scattering experiments, we take the z direction along our conventional x direction. Okay, and we have an influx of Ji particles per unit area per unit time incident from left side. Then we define the differential scattering cross section, which is the ratio of the number of particles scattered into solid angle d omega per unit time to the number of incident particles crossing unit area in unit time. This differential scattering cross section is a function of two angles, usually angle theta and phi, and this d omega is an infinitesimal solid angle in the direction theta phi. So the angle theta represents the angle of scattering and phi represents the azimuth angle. So what we have is, typically we have a target material, then a beam of incident particle, and some of the beam may continue the travel along the z direction without having any interaction, but some beams may get scattered by this scattering object. So what we do is we take a small solid angle. So this angle is given by d omega, or this area, if you consider, and at the end you have a circular area part, and that area is given by r square d omega, where r is the distance from the point of scattering. So this is our point of scattering, and this is a function of theta phi. So this is the typical situation that we are going to consider in scattering experiment. Now, for spherically symmetric potentials, as you know, this differential scattering cross section d sigma by d omega, this will be independent of phi. So this will be simply a function of theta for spherically symmetric potentials. So the total scattering cross section is given by total scattering cross section. Since we know the differential scattering cross section here, the total scattering cross section sigma is obtained by integrating d sigma by d omega over a solid angle d omega. So this is integral 0 to pi integral 0 to 2 pi d sigma by d omega. Sigma is in general functions of two angles theta and phi, sin theta d theta d phi, because d omega in spherical polar coordinates is given by sin theta d theta d phi, and this sigma, this total scattering cross section, is usually measured in unit of barns. So this is the unit, and 1 barn is equal to 10 raised to minus 24 centimeter square. So it's a very small quantity, barn. So this is the unit of total scattering cross section. Now let's see an expression for the scattering amplitude. I told you that basically in all kind of scattering experiments we have an interaction of an incident beam of particles with a target system. So what we basically have is a two particle system. So the Schrodinger equation for a two particle system with the potential V, which we assume it depends only on the relative distance between the two particles, can be written as minus h cross square by 2m del square psi plus V of r psi is equal to E psi. So if you are considering it in the center of mass system, then we have to write minus h cross square by 2 mu, where mu is the reduced mass of the system, small m into capital M divided by small m plus capital M, where this small m is the mass of incident particles, incident beam of particles, and this capital M represents the mass of the target particle that we have in the scattering experiment. And what we assume is that this potential is a function of the relative distance between the two particles. Now we assume that this potential has a finite range A. Thus the interaction between the incident particle and the target occurs only in a limited region of space r less than or equal to A. It's called the range of the scattering region. So when we have target and an incident beam of particles, then what I was telling is that the interaction between the two particles occurs in a region r less than or equal to A, where A will tell you the range of the potential. So if this potential is having only up to this size, then the interaction is limited only within this range. And if a particle is coming out of this range, it may usually go without having any interaction with this particle. So it has a finite range for scattering, and it is that range is determined by the magnitude or the nature of the potential. Potential basically means the potential of this interacting target material. Outside this range, this potential usually vanishes, so potential is 0, and this potential acts only within this range. So in this case, the particle behaves as a free particle before its collision or even at regions outside this range, and hence we can describe it by a plane wave solution. So for non-scattering waves or the incident beams just before the collision, since the potential is zero, you can write the incident beam as a plane wave, or you can describe the incident beam by a plane wave. So the incident beam can be written as a e raised to I k dot r, where k is given by P by H cross, and A is the normalization factor that we will determine later. So this is a plane wave equation, and this is what we assume as the nature of the incident beam, since potential has a finite range. Now as the incident beam is along the z axis, this can be written as, this k dot r can be written as a e raised to I k z. K dot r will be simply k into z. The other components will be 0. The x and y components will be 0. So you will need to consider only this thing for the incident wave. Now when the incident wave interacts with the target, an outgoing wave is scattered out. So when it interacts, then what we have is an outgoing wave which may be scattered in some angle. That depends the nature of the potential. Now in the case of an isotropic scattering, the scattered wave will be usually spherically symmetric, and it has the form of e raised to I k dot r by r, the usual expression for the spherically symmetric wave. In general, however, the scattered wave is not spherically symmetric. Its amplitude depends on the direction theta and phi along which it is detected. So the expression for a scattered wave for a general case can be written as a f of theta phi e raised to I k r by r. So what we are considering here is basically a spherical wave, but the amplitude factor which depends on the angle theta and phi at which we detect this scattered wave, and this f of theta phi is the scattering amplitude, or as the scattering amplitude. So after scattering, what we have is, we have a total wave which consists of a superposition of the incident plane wave and the scattered wave. So after scattering, the total wave can be written as psi is equal to a superposition of the incident wave a e raised to I k z plus the scattered wave, a spherically outgoing wave e raised to I k r by r. Now if it is a spherically symmetric potential, then f of theta phi can be written as just f of theta, as the potential will be independent of the angle phi, or the scattering will be independent of the angle phi. Otherwise these are the functions of two angles theta and phi. Now let's see the incident current density or the flux density. As we have learned in the previous semesters, the expression for the current density in quantum mechanics is given by, let's write Ji for the incident flux of particles, and this is given by I h cross by 2 mu psi I del psi I star minus psi I star del psi I, the usual expression for the current density. And for the scattered beam, let's write Js. This is also given by I h cross by 2 mu psi s del psi s star minus psi s star del psi s. Now if we substitute for psi I and psi s in these expressions for the incident and scattered flux, then we can see that the substitution you have to do yourself. It's a straightforward substitution. What you have to do is, wherever you have this psi I, substitute a e raised to ikz like this term, and wherever you have psi s, substitute a f of theta e raised to ikr by r, which is our scattered wave. So if you do that and if you do some simplifications, you have to do it yourself. What you get is the incident flux density Ji is given by modulus A square h cross k by mu, and the scattered flux density Js is given by modulus A square h cross k by mu r square f of theta phi square. So this is the expression that you get by simply substituting the expression for the incident and scattered wave. Now the number of particles that is scattered into a solid angle d omega along the direction theta phi can be represented by, let's say, dn theta phi. So this is the number of particles scattered into a solid angle d omega in the direction theta phi and passing through a surface element dA, small area, and this is r square d omega. dA is given by r square d omega per unit time. So this is this number of particles dn theta phi, which is passing through a small surface element dA given by r square d sigma, is given by, since we know the scattered current density, this is basically Js r square into d sigma, or you can write dn by d sigma is equal to Js into r square, and if you substitute for Js, this will become modulus A square h cross k by mu into f of theta phi square. If the potential is a spherically symmetric potential, you can write it as A square h cross k by mu f of theta if V is spherically symmetric. Therefore, the differential scattering cross section can be written as d sigma by d omega. So according to the definition of the differential scattering cross section, this is dn by d omega by the incident flux. That was the definition I was given in the beginning of this class. So this is modulus A square h cross k by mu f of theta modulus square divided by, if you substitute for Ji, it is again h cross a modulus A square h cross k by mu. So you can see that this will simply become f of theta square for spherically symmetric potential, otherwise it is f of theta phi square. Thus the problem of determining the scattering cross section reduces to that of obtaining the scattering amplitude f of theta. So once you know the scattering amplitude, then we know the differential scattering cross section, because the square of the scattering amplitude will give you the differential scattering cross section d sigma by d omega. From that you can, if you integrate this over some solid angle d omega, then you get the total scattering cross section. So there are two techniques commonly employed to evaluate the scattering amplitude. One is the partial wave analysis. And the other one is called the Born approximation. So we will be discussing these two techniques of finding out an expression for the scattering amplitude.